Okay, let's check the volume. Okay, so let's continue doing some problems. The equilibrium constant, Kc, is equal to a nitrosolid chlorine and orange yellow compound from nitric acid and molecular chlorine. Is, here it is, 10 times, what a strange number, 10 to the fifth, so at a certain temperature. In an experiment, they got 9.3 moles of NO. So you got 9.3 times 10 to the negative 2 moles NO. You got 1.90 times 10 to the negative 3 moles of Cl2. And you got 8.30 moles of NOCl. Okay, and they all mix in a 2.10 liter container. What is the Kc? That's the first question. And in which direction it will proceed. So the first thing you have to do is convert these moles to concentration. And how? By dividing the liters of the solution. Because when we work with the Kc expression, let's write it down. That's the first thing you should do. Write your equilibrium expression. And it's the concentration of NCCl gas. Okay, and this is to the square is product, right? Divided by the concentration of NO gas to the square 2, and then the concentration of Cl2 gas, and not to the square. No. Okay, so you need the concentration. So let's get the concentration of NO. And the concentration of NO would be 9.30 times 10 to the negative 2 divided by 2.10. And this is liter, so it's moles over milliliter is smaller. So the concentration of NO would be equal to, let me look at the numbers, 0.0443 molar. The concentration of, so now do the calculations, concentration of Cl2 gas, of course, would be 1.90, right? Is this one 1.90 times 10 to the negative 3 moles over 2.10 liters. That's the volume of the container, and it gives me 0.123 905 molar. And finally, the concentration of NOCl, the product, right, equals 8.30 moles. Well, let's do it with the moles here. That I skip it here, that I shouldn't. Divided by 2.10 liter. That's the right way of doing it. And I was skipping to save time. And this is 3.95 moles. I didn't put it, but when they talk about the initial concentration, right? When it's given an initial concentration, the way to express it, the way is with a zero. This is moles. No, I'm doing this. Equal. Now I mess up that. It's mhm, equals 0.123 molar. And here is moles per liter. Okay. When they give you that, when they give you the initial concentration or you are calculating, if you put a zero here, like that's represents the initial, okay, the little zero outside the bracket. So the first question is just asking what is the Q and how do you do the Q? You do the same thing as the equilibrium expression, by the way. So instead of using Kc, you're going to do Qc, which is the same. And just remember, Qc is equal to the concentration of the products, NOCl gas, NOCl gas, to the square, the same thing as the K. But what the difference is that Q, the Q is for non-equilibrium. It could be in equilibrium, then Q is equal to K. And that's what I was going to explain. Cl2 and NO to the square. Cl2 gas, this is the gas. And NO gas to the square. Let's check the equation again. Make sure we got it right. Yeah. Okay. So what we're going to do now is calculate Kc because the second part of the question says in which direction the system proceeds to reach the equilibrium. Okay. So the first thing, like I said, is calculate the Q. But just to make sure the Q, if the Q is equal QC or QP, Q is equal to K, the system is in equilibrium. If the Q is less than K, the equilibrium, the equilibrium shifts to the right. Why? Because at equilibrium, okay, K should be higher, meaning that you have more product form here. If Q is less than K, you don't have enough products. So what it means is that the reaction or the equilibrium goes to the right, and I wouldn't say equilibrium because it hasn't reached it, but the system will produce more product to reach the equilibrium. It produces more on top, so that way Kc, or K in any case, applied to all, pressure, Kp and Kc, is equal to K. That way both of them are equal and it reaches it. Now, if Q is greater than K, that means that you have too much products. So to reach the equilibrium, the equation has to go to the left. to the reactant side. So that way you consume a little bit of the top so you can reach the K. So it shifts to left. Why is it important? Because you don't know in what direction it's going. If they give you all of the reactants and product like here, you don't know where it's going. So when you do the ICE table, that probably we're going to do it in this problem, even though if they're not asking it. When you do the ICE table, you are going to be able to determine, okay, in which direction you're going to plus or minus the x. But let's go ahead and calculate the Q here. And it's going to be QC. We use the concentrations that we had, and it was so 3.95 would be the product. Do you see, molar? Okay, 3.95. I have to bring it back and forward so you can up and down so you can see it. So we're doing the product to the square divided by Cl2 and NO, okay, to the square. So it's going to be 395 to the square. And on the bottom, the concentration, if you remember, of Cl initial that we calculate was 0.123905 molar. And then we multiply this by the concentration of NO to the square. You remember NO was 0.0443, and that's the Cl2, 0.0443. 443 to the square. So QC give us 8.80 times 10 to the 6 times 10 to the 6. Now we're going to compare it to the K, which is 10 by 10, 10 by 10 to the 5th, right? 8.80 times 10 to the 6, right, is greater than KC 10 times 10 to the 5th. Or, in a better way, 1 10 to the 6th. Anyway, QC, okay, is greater than KC. I mean, you have too much product, so we have to shift to the left. Okay. So now that we know that, maybe we can do an ICE table because we have all the yeah, but I know what is going to happen. We're going to have to do a quadratic equation. But anyway, I'm just going to write I'm just going to draw the ICE table. Okay, so you got the reaction here and the procedure. 2NO gas plus CO2 gas is in equilibrium with 2NO Cl gas. Cl gas. So in this case you have the 3 and the concentration of NO was 0. Initial 0.443. This is initial. Change and equilibrium. The chlorine was 0.123905. And the NOCl It's 3.95. Remember, the key is, and this is when it's important that we have to do it. In other problems, we'll finish it doing it. But here, you know that KC is greater than, QC is greater than KC. So we know it's going to the left. So this would be minus 2x, okay, plus x plus 2x. So here would be 0.0443. We add the 2x. Here would be 0.000905 plus x. And here would be 3.95 minus 2x. The reason what I was looking at is that now we could do the quadratic equation to find out the concentrations in equilibrium. But this is going to be a mess. Why? Because we are not going to be able to drop the x, and we're going to have to do the whole quadratic equation. Why? Because look at this constant, equilibrium constant by 10 to the fifth. There's no way you can drop an x here. It has to be very small. From minus 5 down, minus 4, including minus 4 and smaller. But okay, so let's do the next one now. Okay, so we're going to continue with this. The equilibrium constant Kc for the reaction is 88 at a certain temperature. If you start for this reaction, H2 gas, I'm going to rewrite it here, plus I2 gas gives me 2HI gas. Okay, if you start with, okay, they're giving you the Kc, let's write it on here. Kc equals 88.0. Okay, then also they're giving you 0 point, the concentration of HI, okay, equals 0.250 to 50 molar. Okay, and they're asking for the concentration of the three chemicals in equilibrium. So they're asking for H2, HI, and I2. Okay, so where do we start? With the expression first of equilibrium, okay, which is gonna be, I'm doing it like that to save spaces between, it's gonna be Kc for this equilibrium would be, oh, let's do it like this. Okay, Kc would be equal to, okay, the product Hi, always the right side, okay, to the square divided by H2 multiplied by I2. So let's go ahead and put the initial, we're going to have to do the table. We have no choice. So, but the easy thing is that they're giving you the hydrogen iodide to start with, but they don't give you anything else. So this is 0.250. So that means that you got 0 and 0 of each of these. So you know it's going to go to the left because there's nothing here. Automatically it goes to form the hydrogen and the iodide. So it's going to be I had the habit to do it all. So it's going to be minus, you got 2 here, 2x. So to the left it's going to be plus x plus x. So in equilibrium would be x 0.250 minus 2x. So plugging in the x's in the equilibrium expression, we got that Kc, and the Kc is, we said it was 88.0, okay? 88.0. Remember, we're going to find the concentration of the species in equilibrium. So this would be, the HI would be 0.250 minus 2x to the square. And on the bottom, you got x multiplied by x, which is x to the square. So 88.0 equals 0.250 minus 2x to the square divided by x to the square. Now, if you look at this, this is so easy because we can get the square root of both sides. Remember, this is like saying 88.0 equals 0.250 minus 2x divided by x, and all this to the square, and all this to the square. If we get the the square root, because this is to the square, this is to the square. So if on the left side we get the square root of 88.0, this would be the square root of 0.250 minus 2x to the square divided by x to the square. So we eliminate the 2 and the 2 here, the square and square. So the square root of 88.0 equals 0.250 minus 2x divided by x. The square root of 88, let me see if I see it calculated somewhere. Let's do it. The square root of 88.0 is going to be 9.381. So it's going to be 9.381. And now you know the x here is on the bottom. We multiply by x both sides. And it's going to give me that 0.250 minus 2x. So it's going to be 9.381x. Let's add x on both sides. Plus 2x plus 2x equals this plus 2x plus 2x. And that is going to be 938 plus x plus 2x equals 0.250, and it's going to be 11.381x equals 0.250. So x would be 0.250 divided by 11.381, and no x. So okay, As I don't remember where I stopped last time on his show, I'm going to do this. The equilibrium concentration of KC 88.0, okay, 250 is 0.250. As you know, we have 0, 0 here. It goes to the left immediately because you have to produce reactants. You have to reach the equilibrium by going backward in reverse. So Kc equals to, I wrote the expression of Kc equals H equals the concentration of Hi, hydrogen iodide gas, divided by H2 and I2. Okay, so this is, and by the way, the H2, the Hi is to the square, the other ones no. So I do my ICE table based on the reaction going to the left, the equilibrium shifting to the left. So you're going to produce reactants, and it's minus 2x, the change, plus x here. Okay, so it's going to be 0.250 0.250 minus 2x to the square, and what I did is I plug in the values for the expressions, equilibrium concentration, for the Kc. Kc was 88.0. Here it is. 8 Kc is 88.0. Then you have, okay, 250 minus 2x to the square. That's the concentration of Hi, you see, to the square, multiplied by the concentration by x and x, the concentration of each of one of the gases. 88.0, but like I was saying, if you look at this, this is to the square and this is to the square, and it's divided. So you can go and both of them to the square. You can go and get the square root on both sides and the square root of 88. And if you get the square root of this, okay, this would be 1 and this would be 1. So here's the new expression, and it's going to be this. The square root of 88 is 9.381x. And this one would be minus 2x. What did I do here? I took this to multiply the square root of 88.0. So now I add 2x on both sides. Okay, the square root of 88 is 9.381. So I add 2x and it's going to give me 11,381x. Here I add them and I go equals 0.250. Okay, and here x would be 0.250 divided by that. My x is going to be 0.0220. So now we're going to calculate the concentration based on the x and what we have. As we know, the concentration of H2 and I2 in equilibrium would be x and x, and this 0.250 minus x. So this would be the value of x, which was 0.0220, and Hi would be 0.250 was the initial concentration, minus twice the 0.220 gives me 0.206.